These are your 7-1B notes on exponential growth and decay. So we're going to do some simple growth and decay formulas. Before we begin, I'd like to talk about what grows and decreases exponentially. Populations, it goes both ways. Population grows in an exponential curve, and it also decays in an exponential curve. I like to think of population decay. If you think about a few years or a decade ago, when a lot of people were leaving the state of Michigan, and so our population was decaying. Along with that, East China School District, our population was decaying, so it was decreasing, and they usually grow and decay exponentially. It's not linear. And what I mean by that is eventually, even in East China School District, as we lost numbers in the beginning, there was a great number of kids that left because families were moving and jobs. Same thing with the state of Michigan. But eventually, that growth decay levels out and you sort of just balance out. And eventually, hopefully, we'll see that grow over the next few years as well. Bacteria growth is exponential growth. It's not linear, it's not quadratic. It grows exponentially. If you think about a cold or somebody, sneezes in their hand and then touches somebody else, now we went from one infected person to 2 infected people. That person goes and makes contact in another class. All of a sudden now you have contact in 30 more people. So all of those different things. Or we could even say a sneeze within a class goes from 30. Those 30 people could in fact go to 30 different classrooms and infect 30 more kids. So you can see how quickly it can increase. So that's kind of the difference. It's not a constant rate of change. It's exponential. It just skyrockets so quickly. Credit payments and finances, anything involving interest is exponential growth and decay. So the growth formula is A of t, or the amount, the new amount, is equal to little a, which is the original amount, times the quantity 1 plus r to the t. And the decay function or formula, very similar. The new amount is found by taking the original amount, little a, and timesing it by 1 minus r to the t power. And so very similar, one adds and one subtracts. The thing that quantity inside the parentheses is called the growth factor or the decay factor. 1 would represent 100%. So the rate, R is your rate, and A of t is the new amount. That's after the growth or after the decay. So you can always compare the new amount to the original and make sure that it did get bigger in growth or get smaller in decay. Little a is the initial amount, and r is the percent of growth or decay, and t is time. Usually in years if you're talking about finance, but bacteria could be hours, it could be minutes. Populations are sometimes years or maybe decades. Remember, whenever you use r, though, you need to move the decimal 2 decimal places so that you can actually do the math with r. So 85% would be 0.85. So let's go ahead and try a couple of these. I know these are a popular drink among teenagers. So 1 serving of a Monster energy drink has 86 milligrams of caffeine. The average teen can eliminate approximately 12.5% of the caffeine from their system per hour. So every hour, 12.5% of that 86 milligrams releases in your body. So it's no longer in your body, but only 12.5%. So after 2 hours, 24 or 25% will be gone and that sort of thing. Monster drinks, though, if you look at the label, contain 2 servings. So usually what a teenager does is drinks 1 Monster, but not realizing that it's actually 2 servings. So we're going to actually times that by 2 with 86 milligrams of sugar and assume that they're not putting the can down and saving it for later. So 172 milligrams is the number that we're going to use. So write an equation to represent the amount of caffeine remaining after T hours of drinking a Monster energy drink. So we're assuming we're drinking the whole can. Okay, so this is elimination, so it's going to, or well, actually remaining, the caffeine remaining. So we're talking about it's leaving the body at an exponential rate. So this is decay because it's leaving the amount of caffeine. You'll have the 100% of the caffeine from the Monster in your body, and then it will leave from there. So we want to talk about this formula, A of T. The new amount is equal to the original 1 minus R to the T power. So after T hours of drinking, so we don't know how many hours of drinking, we're going to just leave T as a T. So my initial amount, my little a, or original amount, is 172 milligrams. And my new amount would be 12.5% each hour. And so we can just write an equation that represents that we don't really know the new amount unless we have the actual hours. So T is going to be our time. And the rate is equal to 12.5%. 12.5%. So when I put that in there, A of T is equal to 172, 1 minus 0.125, that's my percent as a decimal, to the T. Now, if you don't like how that looks, I know it's growth. If you can think of it, you don't have to write this down, but A of T is just your new value, Y, 172, 1 minus 0.125 to the X power. So you can think of X and Y, but we're just going to talk about it in new amount and time. Draw a graph to represent this function. So if you're going to draw a graph of this, we would simply just, we can use our calculator if we needed to. We could actually calculate 1 minus 0.125 and get our decimal or our base. So Y equals 172.875 to the X power. Since we're graphing, we're going to change it to X and Y. This is my base, and you can see that my base is less than 1, which means it's decay. Now, if I'm going to graph this, we'll kind of just pick some values. So if X is 0, that would raise that to the 0 power. That would be 172. So that's the highest I would be, is 172 milligrams of sugar. So this is sugar milligrams, and this would be time in hours. So after 0 hours, I would have 172 milligrams of sugar. After 1 hour, I'm going to make a table of values. So after 1 hour, I could take that 0.875 to the first power, times it by 172, and I'd have 150.5 milligrams. Before I figure out my scale, I'm going to just plug in a few values. If it's to the second power, I would have to raise 0.875 squared, then times it by 172. I get 131.7. After 3 hours, I will have to cube that 0.875 and then times it by 172. So a big order of operations issue here, or problem. So I can just say, here's my 1 hour, 2 hours, 3 hours. I can even go to 4 hours. So I might just count by 20s to get up here. 20, 40, 60, 80, 100, 20, 40, 60, that's about right, 80. So there's my 172. So after 1 hour, 150, 20, 40, 60, 80, 100, 20, 40, 50-ish. After 2, we're at 131. After 3, we're at 115. And we're kind of leveling off. Thing is, it's not going to drop a whole lot because you only lose 12.5% each hour. Estimate the amount of caffeine in a teen's body after 5 hours. That would be T is 5. So Y is equal to 172 times 0.875 times 5, or to the 5th power. So we have to do that first. Usually when you raise a number to the 5th power, it gets really big, but because this is a fraction or decimal less than 1, it doesn't get very big fast. So it turns into 0.5129, times that by 172, and after 5 hours, there would still be 88 milligrams of sugar. I'm going to show you this on the graphing calculator in class, how you could figure that out. My graph is kind of just a sketch, but 88 milligrams after 5 hours. So even though it starts off dropping quite a bit, you can see that the gaps between those drops changes slightly. The first time it dropped about 20, then it went down about 15, and then it just drops slower and slower each time. That would be exponential decay. All right, and then here's an example of growth. In 2010, there were 85 rabbits in Central Park. The bunnies increased by 12% each year. So if we were to write an equation of the amount of rabbits since 2010, we would say that in T amount of years since 2010. So we would say A of T is my new amount. The original amount was 85. They're increasing at a rate of 12%, so 1 plus 0.12, and then T. Now, whenever we figure out T, years since 2010, we have to keep in mind that we're counting from 2010, not from year 0. So we have to use the 2010 when we figure out that amount T. We're not going to graph this one. We can graph this one in class on the graphing calculator. So that's all I'm asking you is just try to piece together the formula, and then actually you're going to use that formula to answer your practice problem. So lesson summary, I need to know what the little a stands for in growth and decay formulas, and then I need you to calculate the amount of rabbits in 2016. So remember, start counting years from 2010, since that's where our initial data was starting from. Good luck.